Hey, this is Mr. Bean. We're doing another lesson in calculus, and today we will be talking about differentiability. Differentiability means that it is possible to take the derivative. That's what the word means, taking the derivative. Let's find out some stuff about this. So the first thing we're going to do is we have a little graph, and I would like you to take just a second, pause the video, and I want you to write in this option number 1 here, what do you think the equation of this graph is? Okay, so use the grid lines here, write down a little equation. Don't cheat, pause and do this on your own. That is very important for your learning. And most of you probably came up with something like this, something where you have this line with a y-intercept of 1 up to over 1. Okay, that's usually what I get from students doing something like this. Now, it's possible that you might have thought, well, hold on, Mr. Bean, you don't even really have a scale on this. Like, how are we supposed to know what's going on with that? So let me show you what the scale is and see if that changes your graph. So 0.003, what does that mean? Every single line is 0.001. Okay, knowing that, why don't you come up with an equation for number 2? Now, what do you think the equation of this thing is? So put that down on number 2. Pause now. There may have been a few of you who came up with this answer, and some of you might mistakenly have put like a 0.0002, but if you think about this, this is to scale. So you're going up 2 lines and over 1 line. It's like a similar triangle, so it would be the same ratio, up 2 over 1, so their slope's still 2. And then the y-intercept is 0.001. Well, here's the thing. That one is not right either. The right answer is this. Y equals sine of 2x plus 0.001. How in the world are you supposed to know that? When you're zoomed in this close, there's no way. You're not going to know that. And so here's what I wanted to be able to show you. Let me pull this up here. Okay, so here's our graph that I have given you. And what I want you to notice is I can start slowly zooming out. So you can see here, I'm going to start to get a little bit better picture. And even if we're zoomed out here so that it's no longer, I'm now to 0.1, it still looks like a straight line. I'm zoomed in really close. So the further out we go, there we go. Now you can see that is a sine curve. So if we go out here and then we can see it. So the idea is if we're zoomed in really, really close to any graphs, if you get really close to this thing, it just looks like a straight line. So that leads us to our definition of the not definition of the derivative, but defining differentiability. So this derivative is going to exist for each point in the domain. So if a function is differentiable, that means we have a derivative everywhere on that function. Another way of thinking about this is that the graph must be smooth, a smooth line or curve, in order for the derivative to exist. So just think about how I zoomed in really, really close on that thing. If it zooms in close and it's a line, that means locally it is a line. It's called local linearity. That phrase right there is an important one. If we zoom in really close, it looks like a line, therefore we can take the derivative. Because what's the derivative? Remember, it's slope. And if we zoom in, we should be able to see that it looks like a line and then recognize the slope of it. Okay, so there are times when a derivative does not exist, when the derivative fails to exist. So when does this happen? The first place that happens is, move this down, on a discontinuity. So if the graph just doesn't exist, whether it's a jump, a hole, a vertical asymptote, anything like that, if the graph stops, then obviously you can't take the derivative of a point right there when there's no graph and if it doesn't exist. Okay, next one. If there is a corner, or another word for that is cusp. So the corner, cusp, we're going to refer to those same things. So what that means is the graph would look something like this. So if I have, a lot of times you'll have a graph that does like something like this and then takes off. If you have some type of sharp corner right there, or an absolute value graph, that's one that you're probably a little bit more familiar with. If you zoomed in on a corner, it's always going to be a corner. We could zoom in, zoom in, zoom in, zoom in, and it's still going to be a corner. You'll never get a straight line. So if you can't have local linearity, there is no derivative. It's not differentiable. So corners and cusps. And then the last one, which is a little bit harder to visualize, is this thing called vertical tangent. So let me show you what I'm talking about. Do you know how in Algebra 1, if you remember, if we had a vertical line, then that has no slope, or in other words, the slope is undefined. We'd say slope is undefined on vertical lines. So if you have some type of graph, like a cube root, where the graph does something like this, and for just a second, just for that split moment right there, the slope right there, just for that moment, is straight up and down. So if you were to draw a tangent line right there, you'd have a vertical line. If you have a vertical tangent line, then the derivative does not exist right there on that point. Okay, so there's our three areas where a derivative would fail to exist. So true or false? Pause and answer these questions. There's your answers. If you have a function that's differentiable, that means it is a smooth curve or line everywhere on the graph. Okay, oops, that's not smooth. So there can be no breaks, because if we go back to this one, we saw that discontinuities would make the derivative fail to exist. So if it's differentiable, it has to be continuous. Whereas the other way around, just because it's continuous does not mean you have to have a derivative. A good counterexample of this would be that if you have an absolute value graph, that graph is continuous everywhere on its domain, but it is not differentiable right there on that corner. Okay, very, very important true-false questions right here. It may not seem like a big deal, but there will be several questions involved that you've got to be able to answer with those two things.
And here's the last thing from 2.6. This brings in, reintroduces our limit definition of a derivative, and you will identify that these two are specific. Definition of this is a derivative at a point A, whereas this loner down here is the derivative function. That's our our generic derivative for any x value. So this circled one is new, but I'm hoping that you see that it gives you the same information as the top one. It's just that now, instead of saying, here's this arbitrary point A, and then this point that's h units from it, and then let's see what happens with that, that slope as the distance between those two gets smaller. It's saying the same thing here, right? Here's this arbitrary point A, and here's this x that's near it, but let's see what happens as x gets closer and closer to A. So if you look, this one right here is identifying this is A, and this is this x value that's h units from it. And then we want to see what happens as we narrow that gap. Same thing. Here's this A and this arbitrary x near it. So then the question is saying, what's going to happen as my x creeps closer and closer to A? It is the same definition for slope. So this is a new one that occasionally we will use throughout the year. So for example, if I were to see this first statement, the limit as h approaches 0 of f of 7 plus h minus f of 7 all over h equals -2, I know that this is the limit definition of a derivative. So it's the derivative at what x value? 7. So what I know, because this statement on the left is true and equals -2, that, folks, is telling me that the derivative of this function at 7 is -2. The slope of a tangent line when x is 7 of this function f of x is -2. Now, if I saw this notation, it's the same idea. This is also the limit definition of a derivative. So this one is now specifying that the limit as x approaches 5 is 3. That's telling me the slope of the tangent line, f prime of 5, is 3. So the slope of the tangent line when x is 5 would equal 3.